All right, so this week, as I said, we're going to take a look at graphing, okay, sine and cosine functions. There'll be a few problems we look at more tomorrow and Wednesday that are non-graphing, but pretty much the majority of this test is going to be graphing. So we'll start out just by kind of describing some general thoughts about sine and cosine, and then we're going to focus specifically each day on one or two transformations. So today, after we go over the general stuff, then I'm going to get into specific stuff on what's called a phase shift and how you draw that. Tomorrow we'll look at amplitude and vertical shifts. And then the last day we'll look at what's called a period change. So basically these transformations correspond to moving a graph left and right, up and down, there's 2. Stretching it left and right, there's 3. And stretching it up and down, there's 4. Okay. So we're just going to be focusing on sine and cosine. Okay. We're not going to look at the graphs of tangent, cotangent, secant, or cosecant. So these kind of graphs, and I'm going to draw it before I show you the rest of it. Sine and cosine, they're both called periodic functions. Okay. Other functions that you study are not periodic. Okay, when you draw lines, like slope and y-intercept, those aren't periodic. If you draw parabolas, nope, those aren't periodic. So periodic function, at least the ones we're going to look at, look like this. Okay, that's the graph of sine. Just the basic graph. I haven't shifted it left and right. I haven't stretched it at all. That's just what it looks like if you don't do anything to it. Does anyone have an idea what that means? Periodic. Now looking at that picture. Yeah.
It goes up and down.
It goes up and down, and the key is it keeps doing it over and over and over. It just keeps repeating itself. So if I take, let's just take this, and let's just trace this one section right here. That one section that I just traced in black basically describes what's going to be happening forever. Because if I just make a copy of it and put it right here, I get the next section. Okay? If I make another copy of it, I get the next section. So we can just copy and paste that one section over and over, and that describes the whole graph forever. That's what makes it periodic. So that's what I have right here. So what happens is all the y values that you can get, right, which in this particular graph, it goes up as high as 1, and it goes as low as -1, and it starts at 0. So it goes 0, up to 1, back to 0, -1, back to 0. That pattern of y values I said continues to repeat over and over and over. Those y values just keep repeating. Now, how often do they repeat? Well, if I go back to the graph that I had on the other screen, just to show you real quick, they repeat. If I mark that, and go like that. So if I can move that down, that's how often they repeat. Okay, whatever that distance is. So within that space, which we'll describe what that space is called in a second, that's how often they keep repeating. Right. So there's a width there to those x values where I drew the 2 lines. This space is always a certain distance wide, and we'll know what that distance is in a minute. Now you can change that distance. Okay, if I did something like this, let's do sine 4x. So I put a 4 in there. Did I make it repeat faster, like more often, or is it repeating less often? More, right? I took that space that it was repeating and I squished it down. In fact, I squished it down to be 1/4 the size. So it's repeating much faster. And I could do the opposite. I could also make the space that it repeats even bigger. So if I did something like that, now you still get a wave, but it's much more spread out. Okay? And you have to go through a lot more values on the x-axis before it starts repeating. As far as doing what I just showed you right here, that's called a period change. So we're not going to look at that until Thursday. Okay, so the length of the interval, okay, before the graph starts repeating, that's called the period. It's the period of the graph. I think I'm going to mention this later on, but it's also called a cycle. One full cycle of the graph. Starting at 0, going up, going down, going back up. One cycle, or one period. So if you don't mess with the period at all, if you don't stretch it or stretch it out, compress it like I just did, the standard period is always 2 pi radians. So if that's 0, that would be 2 pi. From there to there. So 0 to 2 pi. So the next cycle of this graph would be from 2 pi to 4 pi. And the one after that would be from 4 pi to 6 pi. And then 6 pi to 8 pi. So every 2 pi, you get a cycle. And let me just get rid of this 0.5. And I didn't really mention it, but you can see it. The graph goes left and right. It doesn't just go in the positive direction. It also goes in the negative direction. So between here and here is 2 pi units. Between here and here is another 2 pi units. Which in degrees, what's 2 pi in degrees? How much?
90.
90 is pi over 2.
Is it 45?
45, that's pi over 4. Much, much bigger than that.
360.
360, yeah. So basically this graph repeats every 360 degrees. Okay? Another way to see it is if you go, you can't really do this on a regular calculator, but if I go here, I can look at these values. 90 is when it hits the highest, and we're going to go over these, but that's 0, that's 90, 180, 270, and 360. Okay, so let's just look at them. So 180, that's the one in the middle, and that's when it's back on the axis. 270 is when it's at its lowest point, so 270 is when it's at -1, and then 360, that's the last point, that's when it's back up to 0. Now, if we do it again, we're going to just get these same values. 0, 1, 0, -1, 0, 1, 0, -1, 0. You're just going to keep seeing all those same numbers repeat over and over. Okay, every 90 degrees. Just like this one. Any question on that? Okay, it's not a super complicated graph. It's a wave. And we're going to look at different ways we can transform it. So this part, I've already said to you if you feel you need to write it, but the idea that the graph continues to repeat over and over. That's how I was able to just copy and paste one section of the graph to get the next section, and the next, and the next. I can just keep doing that. It never changes. Okay, and I also mentioned this term, a cycle. So one full period of a graph is also called a cycle. Is anybody in electrical? No. Well, or any shop that deals with electricity, cars too, but that's DC current, not AC current, so that's a little different. But the idea of AC current is that there's a couple things about it. One, it runs at 120 volts. That's usually normal. But the other thing is it runs at 60 hertz. So what that means is if you had a multimeter and you plug it into the outlet, you would see a wave from alternating current, positive and negative, and it would alternate 60 at 60 hertz. What a hertz is it's a cycle per second. So if you look at a graph of electricity, you'd see a wave that goes up and down. And if you looked at it over a period of 1 second, it would go up and down 60 times within 1 second. I can't draw 60, it'd be really close together. But that's what alternating current looks like when you look at a picture of it. All right, so that's where cycle is used a little more. We don't use it as much, but definitely when you talk about electricity, they use the term hertz, which is cycles per second. They don't call it periods per second. That's what they call it. In other countries, that number is a little different. If you go to Europe, their electricity is 50 hertz. So if you plug something in that's not made to run at 50 hertz, you'll ruin it. It won't work. So you got to be careful. If you look at like your cell phone chargers, a lot of them have like that black transformer on it. Well, if you actually read some of the stuff on it, a lot of them say like 120/240 volt, meaning you can plug it into either like US kind of electricity or what they use in other countries. Most newer devices, that's not a problem. They work on either one. But if it doesn't, you got to be careful when you plug it in. So I kind of showed you when we're graphing a trig function, there's really 5 different points you want to try to graph. Okay. They're those 5 points that I just put dots on. So the 5 points are basically where the graph starts and stops. We get what's right in the middle, and then the highest point and the lowest point. And I call those the 5 important points, or the 5 key points to making a graph of a sine wave, or cosine wave. I don't think I showed you a cosine wave. That's the sine. Let me just fix my window. Okay, so there's your sine wave. You get that wave to it. Well, if you look at cosine, let's do that one. Looks pretty much the same, right? It's like the same thing, except it's like shifted to the left a little bit. Okay, that's called a phase shift. So we're going to look at that today. One of the trig functions we're not going to look at is tangent. It's definitely periodic because there's a pattern. You could just copy one section over and over to get the next section, but it's not a wave. Okay, it's a different. It looks a little different. All right, so tangent's not one we look at. Neither is secant. Neither is cosecant. Yeah.
Isn't the difference because tangent goes on forever, but cosecant and sine doesn't go forever on the y, and tangent does?
Yeah, it has to do too with. We're going to get into this more later, but tangent is really bad. If you graph that on the calculator, or you graph that on the calculator, you get exactly the same thing. And the problem with this is when you have a fraction, what number are you never allowed to divide by?
0.
0. So, but cosine can be 0. It can be 0. One example is at 90 degrees. If I take 90, press cosine, I get an answer of 0. So that means when you draw a tangent, something really weird is going to happen if you try to plug in 90 for x, because it would cause you to divide by 0. And that's why you're getting a graph that kind of curves, like it kind of looks something like that. It just went up really high. That's because you're trying to divide by 0, basically. So that's the reason why it looks like that. But with sine and cosine, just looking at them by themselves, sine by itself, it's just sine. There's no fraction there. You'd never divide by 0. Same with cosine. It's just by itself. There's no fraction at all. So that's why you don't have any problem with those. Remember when we did like cosecant and secant? Does anyone remember what you had to do to the ones on the left to get the ones on the right? You had to flip them. Well, if you flip sine, you get that. So if we were to draw cosecant, which is a sine flipped, that one would also look kind of weird because it's a fraction. and you could end up dividing by 0. It looks different than either tangent or anything else I showed you. I'll show you real quick, but we're not going to spend time on it. So this is what cosecant would look like if you drew it. It's periodic because there's a pattern, but it's not a nice wave because it's a fraction. So you could have a problem if you try to divide by 0. And that's why it doesn't look like a wave. All right, so that's another graph we don't look at. All right, so the ones we do look at, we got to find these 5 points. Well, that's 0, and the last one is 2 pi. What's halfway between 0 and 2 pi? Pi. So if you're thinking in degrees, that's like 0, 180, 360, and then a quarter of the way through the cycle is pi over 2. And 3/4 of the way through the cycle is 3 pi over 2. These correspond to 0, 90, 180, 270, 360. It's exactly the table I just did right here. Notice now, but we're getting those errors. That's because I don't have sine typed in anymore. I have something different. Let me put it back on sine. And now that table that you're looking at, that's exactly these points. 0, 0, 90, you're up at 1, 180, back at 0, 270, -1, 360, back to 0. For this week, we do have to get used to working in radians. So I'll just put all these next to it. 0, pi over 2, pi, 3 pi over 2, 2 pi. I have this table written out nicer for you, okay, right down below. So I'm going to give you that table, but I'm just going to write it out a little nicer. I mean, you can copy it down like that too, but I got it better down below. All right, let's see if I can get this on the screen at the same time. Okay, so here's your table for sine. So you've got 0, 0, pi over 2, that's the highest, pi, 0, 3 pi over 2, -1, and 2 pi, 0. Okay. It's exactly the same table I have right there. All right, now let's look at the table for cosine. Okay, so this is what we call the original table. Okay. Anytime that you want to do one of the transformations we're going to learn this week, you always start with this table. Because if you don't know where the graph starts, how can you figure out where it's going to go to? Right, so if I said to you, I want you to take the graph of sine and shift it up 2 units. Up from where? Up from right here. That's where you always start from. That's the basic starting point. Yep.
Is one of the differences that instead of sine starts on negative. Sine starts on 0, right? And
Starts
then
at the
on
origin.
y. And then cosine starts on 1, right?
Yep. Cosine just has a different starting point. So cosine starts at 1. If you look at the graph, and then it goes down to 0, -1, 0, and it finishes where it started back up at 1. So it's the same x values, but the y values are just all off by 1. Okay, so if I ask you to do a cosine problem, and I ask you to shift it left, say pi over 2 degrees, left where you start from? You start from right here. That's the starting table. Okay, so we'll use those tables in every graphing problem we do this week. Any questions on those? All right, so once you know where the graph is going to start from, then you just have to figure out, okay, if I shift it up 1 unit, what happens to all these points that I just circled? If you're doing a sine problem, you'd be using just the table on the left. If you're doing a cosine problem, just the table on the right. So if I were to say shift sine up 1, first I ask myself, okay, when I go up, what values are affected? Well, up and down, that's the y-axis. So if you shift something up or down, you're not doing anything to the x's. Okay? You're just doing something to the y's. Likewise, if you shift something left or right, you're not changing the height of it. If you just move left and right, you're changing the x value. Right? So depending on what transformation you do, either the x's are going to stay the same and the y's are going to change, or the other way around. The y's will stay the same and the x's will change. But one column will always stay the same and one column will always change. Now, could I give you 2 things at the same time? Like say, take the graph and shift it up 1 and shift it left 2. Yeah, I could. We could do 2 things at the same time. But again, since we only spend 3 days on it, every problem will only have 1 transformation at a time. So if I give you a problem where you have to shift up, that's it. You're going to shift up. You won't be doing anything else in the entire problem. Joe, do you have a question?
No, that was my question.
So here's an example of, let's just put up the basic graph again. So there's cosine. You can see how high and low it goes. So watch what happens if I throw a 2 in front. It goes a lot higher and lower. Right? So I just did something to it. I did what's called an amplitude change. Made it taller, stretched it out. Well, I could do an amplitude change and I could compress it at the same time. So now I did 2 things to it. Made it taller and I squished it. Like I kind of think of it like a slinky, right? I just compressed it so you can kind of see more cycles of it. Right? We're not going to be doing 2 things at the same time like that one. Okay, just 1 thing at a time. All right, so now the rest of the things that we look at is going to be focusing on a specific transformation. All right, so we're going to look now at a phase shift. So everything that I gave you up to this point is just kind of general background about sine and cosine. Now we're going to focus on one transformation. So a phase shift is when the graph is translated left or right. You're not doing any kind of stretching. All you're doing is taking what you have and moving it to the left or to the right. So one thing that you have to be able to do for the test is look at an equation and know what transformation it is. Is it, we're going to study 4 of them. Is it a phase shift? Is it an amplitude change? Is it a vertical shift? Now what is it? Well, if it's a phase shift, it always looks like that. Could be sine or cosine, doesn't matter which one. But if you're doing a phase shift, it's when you add or subtract inside the parentheses. And I'll show you an example. I'll graph one on the calculator so you can see it.
Is that a C?
Yep. So C just stands for some value. Right? So this is the amount that you're shifting by. It's the amount of shift, and it's in radians. Are you shifting by pi over 2 radians? Are you shifting by pi radians? You can shift by anything you want. There's usually common ones that we use though. So let's take sine. Here's your graph of sine. And let's shift it pi radians. So if I type in sine of x plus pi. What I'm doing is I'm shifting it. We'll have to figure out, is it going left or right? I don't think you'll be able to tell from this one because, whoops, let me put it in degrees. Let's go, radians, sorry. So put it in radians. Now you'll see it. So there's the original, and there's the one that's been shifted. Because I shifted it exactly half a cycle, you can't tell if I shifted it left or right. You can't really tell by looking at it. But if I shifted it a smaller amount, like let's, instead of shifting it by pi, let's shift it by pi over 4. So it's a very small, that's only a 45-degree shift. Let's look at it now. Now you can tell the red one has been shifted to the left, just a little. And the smaller I make that, let's shift it by something even smaller. Let's do like pi over 6. That's a 30-degree shift. So now the red one is even closer. Okay, it's just barely shifted. All right, so the smaller you make this number, the smaller it shifts. Okay. Notice here the red graph is to the left. What do you think would happen if I did that? Change it to a minus. It's going to go to the right. So plus or minus controls which way it shifts. So now the red graph is going to go to the right a little bit. How much is a little bit? Well, in this case, pi over 6, which is a 30-degree shift. So the two things you want to remember is if you have x minus a value, that will shift the graph to the right. That's what you're looking at right here. X minus a value. And the red graph went to the right. How far to the right? Well, look at the value, whatever the value is. Now you can shift it by whatever value you want. But the common shifts that we usually do are pi, pi over 2, and pi over 4. That's a shift of 180 degrees, 90 degrees, and 45 degrees. Could you shift it by 30? Sure, that's what I'm doing right here. It's not a common one, but you can do it. Could you shift it by 12.7 degrees? Yep. Put in minus 12.7. You can shift by whatever you want. But we have common ones we usually use. And if you have x plus a value, that shifts your graph to the left. Okay, that's the first one I showed you on the calculator, where it was to the left. Okay, a little weird, you might not think of it that way. When I think of a number line, if 0 is here, I think of my positive numbers that way. I think of my negative numbers going that way. Well, that doesn't really help to remember which way to shift. So if you see a negative, x minus, negative shifts to the right. So a minus shifts it right, a plus shifts it left. Okay, out of the 4 transformations that we learned, 2 of them do exactly what you would expect. 2 of them do the opposite of what you would expect. This is one of them that does the opposite. Okay, so minus shifts right, plus shifts left. Just the way it works. Yep.
Is that with cosine and sine?
Yep. Cosine and sine do the exact same behavior. In fact, if I graph, let's graph sine, let's graph cosine. Let's not graph sine twice. Let's try cosine. So there's sine, and there's cosine. They're phase shifts of each other by 90 degrees. They're what we call 90 degrees out of phase. So if I take either the red or the blue and shift it 90 degrees the right way, I can make them line up exactly. Let's take the red one and let's move it to the right 90 degrees, okay, or pi over 2 radians. If I want to move something to the right, do I add or do I subtract?
You subtract.
I subtract. And I can't type in 90 because I'm in radians. But what I just did is I took the cosine and I shifted it right 90. Watch what happens. There's the sine. There's the cosine. They're now the exact same graph. So that's the relationship between sine and cosine. They're phase shifts of each other by 90 degrees. All right. So we know what a phase shift looks like. It's x plus or minus a number inside parentheses. Okay. Now that we know that, how do we use the original table to figure out what my new graph is going to look like? Okay, because we're not using graphing calculators. So how do we make a sketch? Well, it starts by figuring out a table. If we shift with a phase shift, that moves it left and right. What values are affected when you do things left and right? Your x's or your y's?
X's.
The x's are affected. So what that means is the y's are going to stay the same. So when you're trying to graph a phase shift, you're going to go to the original table that I gave you, copy the y values down because they do not change. So there's half the table already done as long as you copy it correctly. If you're doing a sine problem, go to the sine table. Cosine problem, go to the cosine table. All right, so if the y's are going to stay the same, well, that means the x's are going to change. Okay, so let's look at a problem as I show you step 2. What I have there is the same table I gave you in the notes. That's the original table. You really don't need to write that down again. So to figure out what's going to happen to all the x values, look at what's been added, or it could be subtracted. Depends if it's going left or right. So look at what's been added or subtracted. Okay, so if I look at that, I see a minus pi over 2. Okay, I see minus pi over 2. But I have to remember, wait a minute, negative I would think goes to the left, like on a number line, but it doesn't. It does the opposite. It goes to the right. So if I want a graph to go to the right, which I do here, I have to do the opposite of what I see. So if you see a minus pi over 2, you're going to do a plus pi over 2 here, 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 and there. You're going to add pi over 2 to all those numbers. And that's going to shift everything to the right. Okay, where people start to mess this up is once we learn transformations where you have to do the opposite, like this one, and then transformations where you don't do the opposite. So you've got to remember which ones you do the opposite and which ones you don't. This is one you do. Okay, you do the opposite. Okay, so let's go through and make our table. Okay, I made the original table. If you're making a reference sheet for the test, that's probably something you would want to put on it so you can look at it. And when I'm done, I'm going to have 5 x's and 5 y values. Okay. Step 1, look at the equation and determine what kind of transformation it is. Well, we've only learned one so far, but it's the one where you add or subtract inside parentheses. It's a phase shift. So for a phase shift, what values, which column stays the same?
Y.
The y's. So I'm looking at my original table. I'm going to copy them down. No work at all to get the y values. Now the x's are going to change. Look at what's been added or subtracted, in this case subtracted, minus pi over 2, and do the opposite of that to all the original x's. So what am I going to do to all my x's? Yep. I'm going to add pi over 2 because that's going to shift everything to the right, and that's what I said earlier should happen. Okay, so I've got 0 plus pi over 2, pi over 2, plus pi over 2. I'm writing it over there so I can leave a little space, and I'm going to have my final answers inside that box. pi plus pi over 2, 3 pi over 2 plus pi over 2, and 2 pi plus pi over 2. Now we have to do those out. Well, the first one, that's pretty easy. 0 plus pi over 2 is how much? Pi over 2. Alright, so 0 plus anything is just whatever you add. Now the next one, that's also not too bad because we already have a common denominator. What's the common denominator there? 2. So we know the answer has 2. And we have pi over 2 plus another pi over 2.
Pi squared.
If you were multiplying it, it would be pi squared. This is 2 pi. Pi over 2 plus another pi over 2, that's 2 of them. So that's 2 pi over 2. And I'll come back to that in a second, but that's fine for now. The third one. What's the denominator on the 1? Yeah. What's the denominator on pi?
1.
1. There's no denominator there, so we just put a 1. Do we have the same denominator? No. So we can't add those the way they are. What's the common denominator between 1 and 2? 2. So that means the second fraction already has the 2. It's fine. For this one, double the bottom, double the top. Now they have a common denominator. What's 2 pi over 2 plus 1 pi over 2? 3 pi over 2. Okay. Next one already has a common denominator. 3 pi over 2 plus 1 pi over 2.
4 pi.
4 pi over 2. And I'm gonna come back to that one. I'm not reducing it yet because I want you to notice something. And the last one. What do I have to do to get a common denominator?
Multiply by 2. So 5 pi over 2.
Multiply by 2, multiply by 2, 4 pi over 2, plus 1 pi over 2, 5 pi over 2. Now, here's why I didn't reduce them yet. I want you to see something. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. If I was going to draw more, the next one would be 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2, 10 pi over 2. But we're just focusing on one cycle. Okay, when you draw the graph, you don't have to draw something like that. That's a lot of cycles. We're just going to draw one section of it. That's it. Okay, so that's all that this table gives you. Just one section. Okay, so there's our table. So the last thing is to graph it. So when you number your axes, I would not use numbers like 1, 2, 3, 4, 5, 6, because these are pretty lousy numbers. Like this one is pi, which is like 3.14. This one is 2 pi, which is 6.28. So you're going to have all these weird decimals. So the way you want to label your axis, you can label it any way you want, as long as your labels are consistent. Okay? As long as you go by the same thing every time. So what we're going to do is we're going to go by 90s. But we're not going to do it in degrees. We're going to do it in radians. So that's going to be 0. The first one is going to be 90, which is pi over 2. The second one is 180, which is pi. Third one is going to be 270, which is 3 pi over 2. The fourth one is going to be 2 pi. And the fifth one, 5 pi over 2. Okay, sometimes, especially on my graph, it's a little small, so it's hard to fit them all. But that's where the values are. 0, pi over 2, pi, 3 pi over 2, 2 pi, and 5 pi over 2. Okay? I don't like to put the values up that close because when I draw my graph, I'm probably going to end up doing something like this. I'm going to draw right over them. That's why I had them down a little lower. But if you draw through them, it's not a huge deal. Let's move them down a little bit. Okay, and on the y-axis, for that, I think I would go by ones. The highest value is 1, the lowest value is -1. Now, just graph those points. So, pi over 2, 0. Oops, I think I messed this up. I had it off a little bit. So if you're wondering, why did I have 0 as the first one? I think when I did it originally, I had it there. Yeah, that's where I meant to put it. So, pi over 2, 0. Pi, we're up at 1. 3 pi over 2, we're at 0. So that's, so far it looks good. The fourth one, we're down at -1. If you have graph paper, that makes it a little easier. It's kind of hard here, but it's close enough. And then 5 pi over 2, you're back at 0. Okay, so those are your values, and make it look just kind of smooth when you connect it. Okay, it shouldn't look like this. Sine and cosine waves don't really have any sharp points. They look nice and smooth. And there's our graph that shifted to the right a little bit. If you were to draw the original, it would look like this. It would have started here, here, down here, back to there. So what's in red, that's the original. What's in black, that's the new. It's been shifted to the right a little bit. Any questions on that? It's the idea of a phase shift. Okay, so we'll try a couple. We'll try some with sine. We'll try some with cosine. There's no difference other than the table that you start with.
Wait, hold on. So why'd you write like the points that we already started with in the original one? If we made the new one.
Why did I show the original? Just so people could see the difference between the new one and the one we started with.
So the points you put down below, what you actually wrote out, the ones that are marked out are the ones we just made?
Yeah, the ones in black, what we just made.
Yeah, now I get that, but I was just confused.
If you look at the ones in red, 0, 0, there's that one. Pi over 2, up at 1, there's that one. So the ones in red are all the original ones. Yep. And then pi, won't go through all of them, but there's pi 0, there's that one. So on what I think I do on the homework is I have, instead of drawing them on the same graph, I have 2 separate graphs. So you can show me the original and then show me the new one on a separate graph. But the original looks the same for every problem. Okay, any problem where you have to do sine, once you draw the original once, it looks the same way every time. Same with cosine. Once you draw the original one once, no matter how many more problems you have, just copy the original for those. The new graph will look different. The new graph depends on what they have you do right there. Okay, so let's make our table for this one. Okay, so we know that's a phase shift. How do I know that's a phase shift? Besides the fact it's the only one I've typed.
It's in parentheses.
It's in parentheses, and what are you doing in the parentheses?
Adding or subtracting.
That's the key. You're adding or subtracting in the parentheses. That makes it a phase shift. All right. So with a phase shift, what columns doesn't change at all?
Y.
The y's. What are my y's for cosine? Not the same as sine. Yeah?
1, 0, -1, 0.
Yeah. And I didn't mention it yet, but generally the way I grade something like this on the test is this particular problem would be 12 points. You get 1 point for each y value, so there's 5. 1 point for each x value, there's 10. And you get 2 points for the sketch. Okay, the only way you can lose points on the sketch is if you don't label your axis. Okay, that's a big thing. You've got to make sure you label your axis. Because if you don't, I'm going to assume what we always assume, which is each tick mark is 1 unit. And they're not. They're representing 90 units, 90 degrees. Okay. Just in radians. All right, so let's put down our original x's off to the side, and then we'll figure out what we have to do. So Joe, what are my original x's?
Pi over 2.
That's the second one, yep.
0. Pi. 3 pi over 2. And then 2 pi.
2 pi. All right, so we've got our original x's. What am I going to do to all those x values to adjust them? Yep.
Subtract pi.
We're going to do the opposite of what we see. So minus pi, minus pi, minus pi, minus pi, minus pi. Well, the first, the third, and the fifth one, those are quick. 0 minus pi, pi minus pi, and 2 pi, take away 1 pi, is 1 pi. Okay, let's look at the second one. Christian, do I have a common denominator there?
No, you have a common numerator.
I do have a common numerator. Unfortunately, it doesn't help at all. But what's the common denominator between 2 and 1? 2. So what would you have to do to this fraction? What would you multiply the bottom by to make it 2? And then if you do it in the bottom, where else are you going to do it?
On the top.
On the top. So what we have now is 1 pi, take away 2 pi, and the denominator is going to be a 2. What's 1 pi, take away 2 pi?
Negative pi.
Negative pi. Alright, same thing here. Common denominator, that number comes up a lot, 2 and 4 are usually common denominators for every problem. Again here it's multiply by 2, multiply by 2. So 3 pi over 2, take away 2 pi over 2 gives me
Pi over 2.
pi over 2. And if you look at it, if you wrote everything with denominators of 2, you'd see a pattern. The first one is negative 2 pi over 2, negative 1 pi over 2, 0 pi over 2, 1 pi over 2, 2 pi over 2, but it's reduced, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2, and so on. Okay. So if you get that, that would be 10 points right there. 1 for each x, 1 for each y. Okay, any question on that? Okay, so now we'll graph it. Label our axes, remember, just make sure you keep everything equally spaced. So I'm going to start there, that's negative 180, or negative pi. That's negative 90, or negative pi over 2. You don't have to label the axis as 0, I know the axis is 0. That's pi over 2, positive 90, and pi, positive 180. That's all you have to label this time. On the x-axis. On the y-axis, we're going 1 to negative 1, but technically you don't have to label that, because if you don't put labels, that's what it always is assumed to be. Each tick mark is 1 unit. Okay, so let's graph our points. Negative pi, we're up at 1. Negative pi over 2, we're at 0. 0, negative 1. Pi over 2, 0, and pi 1. Now, one mistake that some people do when they draw this is they make it almost like a V. Remember, it should look like this. What you're really sketching is this section right there. It kind of looks like a V, but it's more curved. Okay, so just try to make it look a little curved. So the graph would kind of come in, do something like this, and then it would continue on. You don't have to draw the dotted sections. I just did that to kind of get an idea of the curve. Okay, just don't make it look like that. Okay, any questions on that one? So that's a cosine graph, and it's been shifted to the left. Okay? It's been shifted left pi radians, or about 180 degrees. All right, I've got a program. Let's just take a look before we do the last one. So this program can kind of play what a phase shift would sound like. So it's Bluetooth, so it just has to connect. All right, so that's the sound, just a normal sound. It's 1,000 hertz or a 1 kilohertz sound. That's what it sounds like. So watch what happens as I change the phase. Okay. So this is a stereo speaker, right? There's two speakers in it, left and right. I'm going to leave the right one alone, and I'm just going to try. It's a little weird sometimes, but I'm going to just try to change the phase on the left one and see if you can tell what happens. Anybody notice what kind of happened there?
It sounded like you went from over here to there. I don't know if that
It sounded like it kind of moved.
Yeah.
The sound. Yeah. My speaker did not move. It stayed right there. Now, when I stand here, if I stand right here and do it, I heard nothing at all. Nothing. Standing right in the middle of the speaker. I heard no change. The people that are off to the sides, they probably heard more of a change. Did anyone else not really hear much of an effect? So you notice a couple people right in the middle. They're more centered on the speaker. So a phase shift has to do with how you hear, how loud you hear the sound, but it's not because I'm changing volume. I didn't do anything to volume. Okay?
So it's kind of like moving your speaker to one side as compared to the other.
Well, what it's kind of like happening is you can kind of think of it like this. Here's a sound wave coming at you that way, and here's another sound wave, actually I'm doing a different color, coming at you this way.
Wait, after, can you do it again?
So if you think of the left and the right speaker, what's happening is when I play them out of phase, I'm playing them kind of like that. When the black one wants to go up, the blue one wants to go down. When the blue one wants to go up, the black one's down. So you can think of the two sounds as kind of fighting each other. So what's happening is you're getting this kind of effect where the sounds cancel each other out. And you can't, that's when people said it got louder. Well, if it got louder, then it means it must have been softer at some point too. So the volume is changing because the wave is canceling out. When I move it from here all the way to there, that sound and when I had it at a 0 degree phase shift are exactly the same. If you shift it 360 degrees out of phase, it's back in phase. Right? For some people, this right about here would be about the quietest they would ever hear it, at about 180 degrees. Right? It won't ever completely go away, even though the waves are perfectly fighting each other, because the sound can echo in here. So even if you don't hear it from the speaker right away, you're going to hear it bouncing off the wall eventually and then coming to your ear. So if we could do this outside where we had two speakers and like it was the middle of a field, there was nowhere for it to echo, there might be a spot if you set up two speakers like 50 feet apart where you walk between them. Instead of changing the phase, you actually walk between them, and at some point you would almost not hear anything because there's no way for the sound to echo. But I can't really do that in here. All right. But yeah, you kind of hear it a little different. Like some people said it moved, so I'll just play it one more time. So if I play it there, as I move, it kind of changes a little bit. It got soft right here. It got louder. It got softer again. So it depends on where I stand in the room, but I'll just drag it so people sitting can kind of hear it too. For me, I almost can't even hear it right there. It's really soft right there, standing in this particular spot. Very loud right now. Got much louder.
That's so quiet right there.
Yeah, see, for me, it got much louder there. So it all depends on where you're sitting, and that's why when you're in like a music hall, acoustics are so important, because you could sit there, someone sits there, and they're hearing two totally different things. You think it sounds great, you think it sounds awful. It's just the way the sound is bouncing around. So generally, when they design a music hall, they try to make it so it sounds good everywhere. That's why if you look in like our auditorium, like there's like sometimes panels on the walls that absorb sound. Generally hard surfaces, like boards, pretty much everything in this room, they reflect sound. So it makes it echo. If you hung like curtains on every wall in here, then it would sound a lot less echoey in this room. When no one's in this room, if I like stand up here and I'm like testing my mic or say something, especially if I don't have posters on the wall or anything, it echoes like a lot in here, because every surface in this room is a hard surface. So think of it as like a ball that just bounces right off the surface. Sound does that. Right. Not so much off the white stuff at the top of the room. That's actually why they put that stuff in, because there's like insulation behind it and it's soft. So you think of it as like throwing a ball at like a blanket hanging on a clothesline. You throw it at it real hard, and it doesn't really bounce back. It just kind of hits it, absorbs it, and it falls. That's kind of what that stuff around the room does. It absorbs some of the echo. So any questions on what that sounds like? All right, so let's finish up with one more phase shift. This time it's back to sine, and it's sine with a minus. The first one we did was sine with a, oh, you know what, we did a minus, well, we can do 2 minus, it doesn't matter. We did a plus on cosine, so we did try a plus. Let's try this one. Okay, so it's a phase shift because we're subtracting inside parentheses. What values are going to stay the same? The y's. And after a while, I know you're probably thinking I'll never remember those. I'll need a reference sheet, and you probably won't, because you'll just start to remember what they are. Okay, and same with the original x's. After a while, you just kind of remember what they are. And what are we going to do to all those x values? Add. So this is one of the transformations you have to do the opposite. There will be some tomorrow where we do exactly what you see, but this isn't one of them. So add pi over 4. And what I usually do is, I usually just do it like the first 2, or if I have to, the first 3, and then I see the pattern. And then I just continue the pattern. So then I don't have to keep finding common denominators. So put our answers right in that box. So what's the first one? 0 plus pi over 4. Pi over 4. Second one. Okay, we don't have a common denominator, but what is the common denominator there? 4. So what would we have to do to the fraction on the left to make it have a denominator of 4?
Multiply by 2.
Multiply by 2 on the bottom. Multiply by 2 on the top. So now we have 2 pi over 4 plus 1 pi over 4.
3 pi over.
3 pi over 4. Now I think if we do one more, you'll see the pattern. Okay, that has a denominator of 1. What would we have to multiply the fraction on the left by to have a denominator of 4?
4.
4. So do it on the left. Do it on the top, do it on the bottom. 4 pi over 4 plus 1 pi over 4.
Wait, is every single one going to have a pattern like that?
Mm-hmm.
So then pretty much once we get like 2 or 3, we can just write them out.
Yes. So we'll just get the third one and then we'll go with the pattern from here.
5 pi.
That's 5 pi over 4.
1, 3, 5, 7, 9.
Yep. So the pattern is odd numbers. 1 pi over 4, 3 pi over 4, 5 pi, 7 pi, 9 pi. And they're all equally spaced. They're equally spaced because you can see a pattern. If they weren't equally spaced, you wouldn't see a pattern. Okay, so let's label our axes and see what happens here. Okay, so I'm going to put pi over 4 there. Now we have to be a little careful. What's pi over 4 in degrees? How many degrees is it?
45.
It's 45. So pi over 4 is 45. The next one, 3 pi over 4. Well, that's pi over 4 tripled. So if you triple 45, what do you get?
135.
135. Okay, so let's look at that. From here to here is a gap of 45. That's the way we put it. We put it on the first one. What's the gap from 45 to 135? Yeah?
90.
90. That's a gap of 90. They all have a gap of 90. Okay, and I'm doing it in degrees because it's easier to see than if I do it in radians. Well, that's 45. So where would 3 pi over 4 go? Would it go? Yeah, it would go here. Right? Because remember, the gap is 90. That's 45. That's 45. So the next one is 90 over. And that's how it goes all the way from there. So you're numbering every other tick mark. Right? If you don't, it doesn't work out right. It'd be kind of like doing something like this. 2, 3, 4, 5. You can't do that. Because you're saying from here to here is a gap of 2. That's 0, that's 2. But now you're saying from here to here is a gap of 1. Which is it? Is it a gap of 2 or is it a gap of 1? It's got to be the same gap the whole time. And that's what we're kind of running into here. All right? It's just harder to see it with fractions with pi. So 5 pi over 4, I need one more. 7 pi, well, actually I need 2 more. So let's make this a little longer. 9 pi. Okay. As far as the y-axis, that's 1, that's -1. There's not much change in there today at all. Okay, let's graph our points. So we're at pi over 4 is 0. 3 pi over 4, we're at 1. 5 pi over 4, we're at 0. 7 pi over 4, this is where I should have made my labels lower. I'm going to draw right through it. That's the way it goes. And 9 pi over 4, back to 0. And there's your graph. If you messed up the numbering, what would happen on your graph is, like, let's say you put the second point here. And you said, oh, I'm going to make 3 pi over 4 the next mark. Then what would have happened is your graph would have looked like this. It would have been like too close at the beginning and it would have looked kind of squished. And then the rest of it would have been normally spaced. So if you get a graph that looks like that, you probably you didn't number something right. It was too squished and then stretched out too much. Right? To me, that looks good. It looks symmetric. So that's how it should look. Okay, any questions on that? Okay, so that's our phase shift. All right, so the homework tonight, I'll put it in the video. In case you lose it, it'll be 5 questions. And it'll be on a separate worksheet.